ETM Hotel, Rennie Sean. Welcome in peace. My name is Sean. I'd like to thank everybody for tuning into this episode of Science with Sean. Uh, Please like the show, share the show, tell a friend that we're actually live. I know I haven't been live in a minute. I've been tied up doing a lot of historical uh, legacy cleaning up regarding other subject matters and kind of got distracted from the cause, but I'm back. So, I just figure out how to manage my time in a different way to probably doing the shows a little bit differently than before so that I can make sure, the obligations are met on all ends. However, if you have not gotten your copy of What SARS-CoV-2 Taught Me, the link for the book is in the description. I know there's several of you that have not purchased a copy of it yet. People that I know, and some of you who have been saying that you're going to purchase it and you haven't copped it yet. So the link is in the description of the video. I do want to say that I will be live on the SAR Imhotep's channel this Friday at I believe it's 8:15 Central, 9:15 Eastern. He will be interviewing me in regard to the book What SARS-CoV-2 Taught Me, which you can pick up at Same Tree Different Branch Publishing. So please make sure that you go order it right now. I get the book out to you. You'll have it before Friday in some instances, depending on where you live. I do want to say peace to everybody in the chat and those of you who may catch the replay. Today is about adaptive immunity. That's right, part of the immune system that makes sense. Adaptive immunity. And that's not it, just immune memory to SARS-CoV-2. So what we're going to do is we're going to get into a lecture, right, from the experts. And we're going to see what they're saying on the subject matter of adaptive immunity, how your immune system is working, especially in regard to to SARS-CoV-2. And we're going to see how on par we are with our research and all the information that we've actually learned. If you are a basketball fan, I will tell you now that Duke is leading by 5 against Kentucky. And this is a 9-10 matchup in the opening night of the State Farm Classic. So please like the show, share the show, tell a friend, tell a friend. I don't know if I'm boring and not going to have a lot of people in here today, or, some of y'all may have already went to bed, but I'm here, pop-up shop. Before we get going, everybody knows that I've been studying a book or a text called Scientific Integrity. People have seen me post some stuff out of the book or a quote or mention in regards to people challenging the fact that not challenging the fact, but challenging the position that I actually take in regards to the published work of What SARS-CoV-2 Taught Me. You have people doubting or thinking or assuming that I think that I'm an actual scientist. No, I'm a researcher. But in the field of science and in science integrity, research or researchers are prominent in this field. As a matter of fact, scientists encourage people to be researchers. They not only advocate for more scientists, but they advocate for more researchers who can understand what they're dealing with and understand the methodologies and how they come to a conclusion and all of these things. So when you're reviewing data and dealing with the information, that you actually can come across to someone who may not know these things and communicate where they fall short. So they encourage this stuff. And basically, I like the way that the book is designed, the text is designed, and things of that nature, but it continues to teach. And really, it just harps on methodology. So before we get going, though, I do want to share with you something that I found pretty interesting in what I was reading. And I'm going to share it with y'all before we get into it. All right. Now, it says, in recent times, headlines, news shows, books, and magazine articles speak of stolen viruses, science under siege, falsified results, scapegoats, whistleblowers, scientific hoaxes, misconduct investigations. What has happened? An editorial in Scientific Journal asked, when did we become so naughty? Are increasing numbers of scientists acting unethically and dishonestly? Can it be profitable to fabricate or falsify results? Has the competitive nature of scientific research placed pressures on scientists that led to misconduct? Before addressing the issues that stem from such questions, you have to talk about doing research and know about researchers. So I found this quite interesting. The mere fact that when you're talking about scientific integrity, that researchers help answer questions in a field that they don't necessarily have to be experts on to advance science. Says understanding as best as we can how scientists do research is critical. If we are to define scientific misconduct, but gaining a feel for how science is done is not easy. Science, after all, is the work of humans, and humans are fallible, impressionable, impulsive, and subjective. They can fall prey to self-deception, rationalizing their actions in ways that mislead themselves and others. The term sloppy science is frequently used to describe some of the behaviors, but the distinctions between sloppy science and scientific misconduct can be nebulous. Those seeking clear-cut answers commonly invoke the idea of deliberate deception as the defining element in misconduct. But proving that someone made a conscious decision to falsify or fabricate data or to steal another's ideas can be extremely difficult, if not impossible. Nevertheless, each year we find government websites reporting annual summaries or closed misconduct cases where guilt was established from the evidence or admitted to by the accused. In these times, both scientists and the public have a heightened awareness of the accountability that goes with doing research, especially in the biomedical sciences. Scientists facing the difficulty of acquiring grant funds justifying their use of animals in biomedical research and explaining to the public why the war on cancer still hasn't been won are sometimes challenged to defend the cause of science and the expenditure of the public funds. On the other hand, the public regards science as a definitive vehicle for uncovering truth. They become confused when scientists disagree with one another. Listen to this, because this is where we are. They cannot understand how scientific facts can be disputed. Yet definitions of scientific misconduct frequently affirm the scientists will have honest differences in interpretations of judgments of data, and that honest error in science does occur. The public has difficulty understanding that the scientific method can be erroneous results. In advertising, for example, there seems to be no greater virtue than to claim a product was scientifically tested, or better yet, scientifically proven to achieve results. The public finds the idea of scientific truth an attractive one. After all, when it comes to much of the research that occurs in universities, institutions, government labs, and other places, the public is paying the bills with their tax dollars, and they want their money's worth. So when new facts cause scientists to change their previous interpretations and conclusions, the effect of public is disquieting. Tracking newspaper headlines associated with the effects of oat bran consumption on cardiovascular illustrates this point. In 1986, typical headlines referred to oat bran as the next miracle food, and the public was advised to know your oats. Then in the early 1990s, some headlines declared oat brands claimed weakened. or they spoke of the rise and fall of the old brand. But as the decade progressed, so did our understanding of how old brands works. Results of peer-reviewed clinical trials began to convince the scientific community that the regular consumption of oat bran has positive effects. We've learned that the soluble fiber of oat bran absorbs bile salts in the intestinal tract, exerting an effect of cholesterol homeostasis and probably lowering cholesterol blood levels. From this comes the reasonable expectation of decreased atherosclerotic plaque formations in blood vessels and clear benefit of cardiovascular health. And so the headlines once again changed, reporting that oat bran study says cholesterol lowered and lots of oat bran found to cut cholesterol. One headline reflected the frustration the public must have felt, confused about oat bran, but this is seemingly confusing stream of information is just an example of science working the way it's supposed to. The very nature of scientific investigation makes the accumulation of new information and the interpretation of existing data subject to periodic change. Why am I even saying this right now? Because we're in an era right now of where we're dealing with a pandemic. Inside of that pandemic, we were able to watch the scientific method work in real time. When information was presented, then retracted, we knew that later on it was falsifiable and they had to go back to the drawing board. However, some of the people who didn't see that, didn't know how science worked, projected frustration. They began to hold on to that which was already retracted and keep it, and it continued to circulate. For example, ivermectin. Ivermectin, what Aaron Rodgers took, and now he fired his healthcare specialist or whatever. Little suspect, little too late to be doing that. And then claimed that he was allergic to some type of ingredients that was in the mRNA vaccines, which lack ingredients. So, just based on what I'm saying, hopefully you're able to walk with me on how science works. For instance, vitamin D, vitamin C, and zinc initially was thought to cut the risk of death, right? Not stop the virus, not stop the risk of infection, not prevent it, none of those things, as a treatment to prevent death and hospitalization. However, it proved through clinical trials not to be valid, right? There was no changes. They saw no difference. However, you still have a section or a community of people out there that are projecting and promoting vitamin C, D, and zinc. Alternatives. Instead of a vaccine, promoting the vaccine for which will help you, right? Prevent you from hospitalization and death, right? At a large percentage, 99.998%. But people still have misconceptions about vaccines and not understanding vaccine science or the scientific method as a whole. So let me continue before we get into the bill. Scientists recognize that this is how science normally works. But in general, people outside of science do not have this same understanding. Disagreements, errors, and new interpretations of results are sometimes reported to the public by media. It is easy for such reporting to be misinterpreted. The debate over emerging or evolving scientific knowledge can be seen as confusing or interpreted as accusation. This may even cause some to question the integrity of science. Compounding this problem is the common held stereotype that David Goldstein calls the myth of the noble scientist. This myth holds that scientists must be virtuous, upright, impervious to human drives, such as personal ambition, and capable of misbehaving. Goodstein recognizes science as a human activity that has hypocrisies and misrepresentations built into it. As scientists, we become accustomed to such behaviors and often don't even recognize misrepresentations. Goodstein argues that this myth of the noble scientist does science a disservice because it blurs the distinctions between harmless minor hypocrisies and real fraud. In summary, the human behavior that is part of scientific research may influence how that research is done. The effects of behavior patterns may vary, as may the degree to which their perceptions by scientists of the public is gauged as good or bad. Sorting out these efforts is likely to be a challenge for scientists and a source of confusion in non-scientists. Failure to appreciate the element of human behavior in the performance of scientific research can lead to misunderstandings that may confuse normal activities with inappropriate behavior. That's what we are. We have a community of people that are misleading. They're misleading on purpose. People are being pretty much they just being led in every direction possible, and it's crazy. So we're gonna go ahead and get the bill started today. I didn't know if anybody would show up. I wasn't expecting a lot of people, but my bad, I'm trying to fix something. We're here now, so let's deal with the deal. Again, man, like the show, share the show, tell a friend, we live. You know, since the whole debacle with and Zynga and all of that, I don't figure many people even tune in, you feel me, or support, but it's okay. Hold up. Before I even I don't want no copyright disclaimer. Under Section 107 of the Copyright Act of 1976, allowance is made for fair use for the purpose such as criticism, comment, news reporting, teaching, scholarship, and research. Fair use is permitted by copyright statute that might otherwise be infringing. Let's go.
And together with Richard Young and Canon Overhaul, we have organized this MIT course on COVID-19, SARS-CoV-2, and the pandemic. On behalf of the three of us, thank you for joining us today. And as you know, the purpose of this course is to learn what we know about this virus and the pandemic from the best scientists around the world. And today I have the great honor to introduce a wonderful colleague of mine, Professor Shane Crotty. Dr. Crotty is an internationally recognized as an expert in immunology and vaccines. Shane's lab focuses in understanding fundamental principles that drive the development of long-lasting antibody response to harness that knowledge for vaccine design. Shane has published over 150 scientific papers in peer-reviewed journals in virology, in immunology, and vaccines. And he has been for the last 5 years among the top most cited researchers in the field. Just one example of the seminal papers Shane has contributed on COVID-19 is the one that he published in collaboration with Alessandro Sepe at La Jolla Institute of Immunology, that he has gotten the highest public attention, getting for a paper published in Cell ever. Shane is not a stranger to MIT. Indeed, he has completed his bachelor degrees in biology and writing in here. And then he has moved to the University of California, San Francisco, and set up his own lab in 2003, sorry. And Shane was the recipient of a few colors in biomedical research, and he has received the 2012 American Association of Immunology PD Bioscience Investigator Award. And in 2019, he has received the Cancer Research Institute Frederick
Jukundo, and thanks for that generous introduction. Yes, I'm going to talk about SARS-CoV-2 and particularly our understanding of adaptive immunity against the virus, spanning multiple different components of adaptive immunity, as you'll see me described. And it's a real pleasure for me to talk to this course because, yeah, I was an undergrad at MIT and loved my time there. I was course 7 and course 21W, so there you go. And so it's, yeah, like I said, pleasure to talk to you all. And as mentioned, this is where I am now, the La Jolla Institute for Immunology. It's a nonprofit research institute on the University of California, San Diego campus. And the first study that I'm going to tell you about is this one, which is done like almost everything that I've done in COVID-19 in close collaboration with Professor Alex Setti, also here at LJI. And here we were trying to get at this question early on in the pandemic of do people develop immunity to COVID-19? And here's the front page of that paper, or if you prefer a live action view, here's Tony Fauci holding up a copy of the paper as he attempted to explain T cells to.
For anyone who may be unfamiliar with what Tony Fauci is holding in his hands, we actually have this paper on another show, but it's relevant to bring this information up because someone the other today had asked me about vaccine immunity and people saying that the efficacy of the vaccines is waning and so on and so forth. And that's not necessarily true. These vaccines are working because they're preventing hospitalizations and death. Even against Delta, the vaccines were working. The thing about it is people are so hung up in efficacy. And this is one of the reasons why top virologists were saying, look, we don't need to boost our way out of something or try to control things by boosting. We need to immunize. We need to vaccinate more people versus boosting. Booster shots. They felt like that the vaccines would serve more of a purpose if we just vaccinated more people. And that's true because we don't have the potential of Delta Plus being a relevant variant that could be more transmissible and more infectious. Or we don't have new variants popping up and adapting because that is what viruses do. But let's continue.
Politicians. And that study got attention for a number of different reasons, and I'll walk you through it. There was a lot of fear and uncertainty in the spring of 2020 about many things related to this novel coronavirus, but one of them was a concern that either people didn't make immune responses to this virus, that is adaptive immune responses to this virus, or developed immunity to this virus, or that people made very strange immune responses to the virus. And also at the same time, there was a lot of interest in obviously developing a vaccine against this virus. And normally when developing a vaccine, you would want to know in advance what kind of immunity is important against the disease, so as to try and design a vaccine that would elicit that type of immunity. And obviously in a world on fire type of situation like the COVID pandemic, it made sense for people to go ahead and start vaccine development efforts. But we wanted to try and generate data as quickly as possible that might help inform what paths would be more helpful than others. Okay, and so what we considered were a couple of things. So one is that to really determine all the mechanisms of protective immunity against a given virus frequently takes many years. A decade would be unsurprising. And so formally answering that would be a hard problem. But what we considered was that, well, this is a virus that causes acute infections that resolve or cure in most people. And so that probably reflects people who get infected by the virus have significant infection. And then those people make an adaptive immune response that then clears the infection. And that most likely, in the absence of that adaptive immune response, people would not have cleared the infection. And so as a first pass best guess, if you will, about what kinds of immunity were important against this disease, we could ask, well, in these average cases of COVID-19, i.e. non-hospitalized cases, cases where people got infected, got some symptoms, but then cleared the infection, what kinds of immune responses did they make? Because those were protective immune responses. And in doing that, we wanted to make sure we measured all three major compartments of adaptive immunity. As probably already mentioned to you, so innate immunity is the part of your immune system that essentially sort of quote unquote generically recognizes whether something's a viral infection or a bacterial infection. The adaptive part of your immune system is the part that specifically recognizes a given virus or other type of infection. And that immunity really consists of three major components. And antibodies, which are made by B cells, these, we definitely wanted to measure those because they're important in almost all currently licensed human vaccines. But the other two branches of adaptive immunity are also known to be important for a variety of viral infections. And those are two types of T cells. So one are the Cd4 T cells, also known as helper T cells. These are critical for antibody responses, and I'll come back to that. I.e., in general, you don't get neutralizing antibody responses unless you have a Cd4 T cell response. But these T cells actually have a variety of functions, and in particular, in viral infections, they can have direct antiviral activities. And it had been known previously in the Sars mouse model, the Cd4 T cells could actually protect animals independently of antibodies against that other coronavirus, which made them of interest. And third, last but not least for sure, are the Cd8 T cells, also known as killer T cells. These are important in many viral infections. There are many viruses that are essentially impossible to clear without a Cd8 T cell response. And the simplest way of thinking about this is that antibodies are good at stopping viruses outside of cells, but once viruses are inside of cells, once you have active infections, that requires T cells, because T cells will recognize infected cells, and killer T cells in particular will recognize infected cells and kill off those cells. And for different viruses, you need these different branches of adaptive immunity to differing degrees. Sometimes a virus, it's all about the antibody response, and sometimes a viral infection, it's all about the Cd8 T cell response. I would say more often than not for acute viral infections, it's a mixture of all of these. They all have contributions to play. And I think a useful analogy is branches of the military, where you might have the Air Force, the Navy, and the Army, and they have different weapons, right, different tools. They're particularly good in certain environments compared to others, but they also can really compensate for each other as well as work together. Okay, so we wanted to measure all three of those in people who had recovered from a quote-unquote average COVID-19 disease. Okay, and the biggest challenge there was the T cell side. It is challenging to identify virus-specific T cell responses in people for a couple of reasons. And one, I like using this Lego analogy for. So if you had a Sars Cov2 virus made out of Legos, it's the red Lego on the top is the spike, and that's the target of the key antibody responses. But the T cells recognize individual pieces of the virus. They recognize individual Legos, and in fact, they can be individual Legos from anywhere in the virus, including parts that aren't part of the physical virus. They're only expressed by the virus in infected cells, i.e. the replication machinery and other genes. So this is a virus with about 25 different proteins, and we didn't know which of those had T cell responses, and even within those, which little piece of each protein were the actual targets of the T cells. And on top of that, humans are very immunologically diverse in terms of T cell responses. So my T cells recognize different Legos than your T cells, even though we might both recognize, say, the spike protein. And luckily, here at LGI, we have Professor Alex Cedi, who's probably the top 1 or 2 expert in the world at computationally predicting and then experimentally identifying human T cell responses. And so he went and made predictions and synthesized predicted epitopes, and then we worked together to measure these 3 immune responses in these people. And so here's a composite view of what we found, considering multiple different viral antigens. So we found that about 100% of these people made antibodies against spike, and that was good, and other groups had observed that. And what we were adding to that were doing that and the T cells in the same individuals. Okay, and so what we saw was that 100% of the individuals made Cd4 T cell responses to the virus, and most individuals made a Cd8 T cell response to the virus. And a key, well, I'll come back to it. So in general, looking at the overall picture, it was actually good news. It was really antiviral immunity that matched expectations. That the magnitude and functional characteristics of these responses all looked good. And it actually didn't look like a particularly difficult virus to stop, in the sense that these immune responses weren't massive. It hadn't taken a huge response by people to control the virus. In addition, for a big concern of ours going into this study was surrounding the spike protein, because it was clear already that essentially almost all of the vaccine programs ongoing were against spike. And one of our concerns was that spike was clearly an important antibody target, but if spike was a poor T cell target, that would be a big red flag for a spike-only vaccine. And thankfully, what we observed was that spike was actually a good target of both CD4 and CD8 T cell responses. And so we concluded that if you were to go forward with a single protein vaccine, spike was a good choice, because not only was it a target of antibodies, but it was a target of both types of T cells for this particular virus. And to show you a little bit more raw data, we actually looked at T cell responses to every single one of the viral proteins, because we really wanted to make sure that we had a good sense of what type of immune response was going on to this virus, and that there may be particular targets that were better than others. And what we observed, and so we ranked them in here, what we observed was that spike was one of the top T cell targets, and that there were also very broad.
I wanna run this back real quick, because he said something that was key, and especially when you're creating a vaccine to target how to stop something. Listen to what he says.
And that there may be particular targets that were better than others. And what we observed, and so we ranked them in here, what we observed was that spike was one of the top T cell targets.
Spike was the top T cell target. The spike is the top T cell target.
And that there were also very broad T cell targets. We observed T cell responses to almost all of the proteins in the virus, which again was a positive sign, indicating that the immune response was very capable of recognizing this virus in many different ways. Okay? And so the tools to measure those T cell responses, we've been proud to share with many labs around the world, and Alex Cedi, who takes the lead on all of that, is also very keen and happy about the fact that he's shared the reagents with people with labs on 6 different continents. So in thinking about immunity to this virus, these are very important topics. So do antibodies, Cd4 T cells and Cd8 T cells all contribute, and how much do they each contribute, and how does that impact how we think about protective immunity after infection and protective immunity after vaccines? So I'm going to give you a short version of all of that and just a big picture view of my perspective on this topic. We don't have all the answers, and immunology is very complicated, but here's my best assessment, okay, of what are mechanisms of protective immunity against this disease, and here are the 3 bullet points I will go through quickly, okay. First, when I consider immunity to any infection, I always like to start with, well, what's the virology what's the biology of the virus, and what's the anatomy of the disease? And for this virus, really we're talking about a virus that replicates very quickly in nasal passages and the oral cavity, with transmission within about 4 days of infection, even before symptom onset, right? And infection in those 2 tissues is really where you get this spectrum of disease, everywhere from asymptomatic through to cold-like, flu-like symptoms. Okay? But really, the disease that we worry most about is the disease in a different tissue, and that is the lung tissue. It's in the lungs where you get the pneumonia and the ARDS and the fatalities, and this is where all of the hospitalization level disease comes from. And notably, while this is a fast infection of these 2 tissues, it's a relatively slow infection, slow disease of this tissue, which is why we talk about hospitalization data out at day 21 post-symptom onset, which is a very long time from day 4, and not the same as compared to certain other diseases. And that affects which parts of immunity can potentially control this virus in different compartments. So for example, if you're trying to stop the virus in these 2 tissues, you have to do so quickly, and so antibodies are probably important in that case. And a simple way to phrase all of this is that, look, it's a race, okay? This is a race between the virus and your immune system, and speed matters, and so you have to keep the kinetics of these different things in mind. And so antibodies are great because they're already there at the front door. They're your first line of defense, and we'll come back to this a bit. So the simplest option for any vaccine development is high-level, long-lasting neutralizing antibodies. Okay, this is a virus that's clearly susceptible to neutralizing antibodies. Antibody transfers have clearly shown the ability to protect, but we pay attention to all the other parts of the immune system because keeping in mind, well, what if you can't have high levels of antibodies, or if you don't have high levels of antibodies, or if they're not that long lasting, or if they're obviated by viral variants, right? While antibodies are your first line of defense, do you have other lines of defense that can stop this virus and either prevent symptomatic disease, or prevent serious disease, or prevent transmission anywhere on that spectrum of disease? What types of immunity could be involved? A final thing that I'll say about antibodies is it's much easier to measure antibodies than T cells. And so antibodies are also a helpful correlate of immunity. That is, you can measure antibodies and they might correlate with other parts of the immune system that are contributing protective immunity. And so by measuring the antibodies, you also have a surrogate measure of other parts of immunity that may also be contributing. And antibodies are clearly a correlate of T cells because the neutralizing antibody responses, as I already mentioned, almost always depend on Cd4 T cells. You generally don't see a meaningful antibody response unless there was already a T cell response, a Cd4 T cell response. And notably, that's actually a subset of those CD4s, and I'll come back to these because of their importance in this topic. And so antibodies definitely important, but various lines of evidence also point to protective contributions of T cells against this disease. And here's a list of some of the types of evidence available showing that indicating that T cells have a protective role to play in this disease, either CD4s or CD8s, or the combination thereof. And these come from data in both monkey models and from humans. I don't have time to go through all of that. I'm simply going to highlight one study, which happens to be from my lab. That's a representative one, where we asked, in the context of acute COVID-19 and hospitalization, was there a relationship between immune responses and disease severity? And what we observed was that actually people who tended to have the worst outcomes were people who were largely failing to make a good adaptive immune response, i.e. they
Through a study, they have determined that people who were having a worse response were those people who were not building any type of adaptive immunity to SARS-CoV-2. See, these are key points, right? And this also shows the trickiness of the immune system, because the people who suffered the most ended up having better protection against either reinfection down the line versus people who had some type of adaptive response earlier on and had, like, what I want to say, like, minor symptoms, right? That reaction wasn't great enough to create any type of lasting antibodies. So people who just, who were asymptomatic and just got infected, they would have these little, they would see reinfection rates increase. But let's listen to it again.
Disease severity. And what we observed was that actually people who tended to have the worst outcomes were people who were largely failing to make a good adaptive immune response, i.e. they were lacking a Cd8 T cell response or a Cd4 T cell response or an antibody response. And the asterisks here indicate statistical significance, which was that there was a statistically significant association between the presence of Cd8 T cells or Cd4 T cells and better outcomes. And interestingly, that was associated with age, and it's very well known that age is a major COVID-19 risk factor. And our data indicated that adaptive immunity shortcomings are part of that problem of aging. And that seemed to be related to poorly coordinated T cell responses. And interestingly, one of the things we know about aging is that the older people get, the fewer naive T cells they have. And so I'll expand on that briefly so you can understand T cells. And so one of the things we did is we looked at this cohort of individuals that we had and asked, well, did age correlate with T cells? And indeed it did. So the older people were, the fewer the naive T cells that were detectable in the blood. And there was a correlation with disease severity in the same way. Okay, the fewer the naive T cells in the blood, a higher association with disease severity. So that was an indication that this may be at play. And so this is data from another lab, the great Donna Farber, who's really done some wonderful human immunology. And so T cells are born in an organ you have called the thymus. And here's T cell birth, basically, by...
Where are T cells born again? T cells are born in the what? It's on the screen. I know there's a delay, so I'm trying to see if anybody gonna be able to answer. But where are T cells born again? T cells are born in the thymus. I'm gonna run it back.
another lab, the great Donna Farber, who's really done some wonderful human immunology. And so T cells are born in an organ you have called the thymus. Okay? And here's T cell birth, basically, by a
Thymus, Thymus. It's on the screen. Human thymus. Right here, you see where my arrow getting big? That's where the T cells are born in an organ called the thymus. Right here, you see it? That's the thymus. You see it? You see that? Purple? Right there. Look. Thymus. Now let's go look at it, the anatomy. Thymus. You see it now? That anatomy ain't no joke, bro. You see it? You know, some of y'all be feeling y'all chest, right? Because I know I do it sometimes. But right there. It makes sense now. Now that you know where it's located at now, right? See? From all the images that we have on the screen, we can identify it a lot faster now. Now, think about what's being said. Remember, coronaviruses are respiratory viruses. However, they attack differently. COVID-19, this disease, well, SARS-CoV-2. Sorry, I'm correcting myself. SARS-CoV-2. This virus behaves totally different than other coronaviruses, and it attacks more than just the respiratory area. But look at where the T cells are created. If the T cell, dang near right where your lungs are. Let's look at a human image. Let's see if we can get a really good picture. If it's gonna show us. Nope, that didn't show us. I'm just trying to find us a good little picture, so we're not looking at an animated version. Nope, they ain't gonna let us see it. Boy, they stingy with the images. Well, I tell you. But anyway, y'all get the gist of it. I don't want to gross nobody out because I could put up an actual video and we can see it in the human body real time. But I don't want to gross y'all out. No more than I probably already have.
Age in years, and you make lots of T cells, but then over time the thymus becomes much less functional, and you start making far fewer, down to potentially almost none, T cells later in life. And so what we concluded from that is that at least some individuals, as you get older, end up with fewer and fewer naive T cells. And this is the source of your new virus-specific T cell responses. And so it makes sense that if you have fewer T cells, maybe you don't make as good or as fast as a T cell response to a new virus, such as SARS-CoV-2, putting you at risk of, in that race between your immune system and the virus, you're at more risk of the virus getting too much of a head start because you didn't have as many T cells to start with. And I'll go ahead and say, one of the good things about this is that vaccines get rid of the race, right? So if the problem is that you have the potential.
No, you did not say that. No, you did not sit here and say that. and think I was just going to let you keep on talking. No, you're not going to sit here and say that vaccines do a better job than someone being naturally infected because it takes longer for them to build some type of immune response. No, you was not saying that, Dr. Crotty. Was you seriously about to say what I think that you was about to say?
About this is that vaccines get rid of the race, right? So if the problem is that you have the potential to make that T cell response as an older individual, but you make it slower than a younger adult, well, then a vaccine can solve that, right? Because you get to make that T cell response before you ever see the virus, sort of on your own time.
Interesting. So a safer way to protect yourself against a virus is to get a vaccine. And especially if you're older, it would help you be able to recognize the virus a lot faster and protect yourself a lot better. Even the younger ones, it does the same thing. However, I don't want to put no words in nobody's mouth, but I want y'all to hear it again. Golly, man.
About this is that vaccines get rid of the race, right? So if the problem is that you have the potential to make that T cell response as an older individual, but you make it slower than a younger adult, well, then a vaccine can solve that, right? Because you get to make that T cell response before you ever see the virus, sort of on your own time. And so with those ideas in mind, I consider that it's reasonable to consider that hospitalization level COVID-19 is prevented by any decent combination of antibodies, memory B cells, Cd4 T cells, and Cd8 T cells. And that's because antibodies are probably helpful, or definitely helpful, at stopping the virus at the front door. But if the virus gets in and does start an infection, there's actually a lot of time before you end up with a serious lung infection. And that gives plenty of time for your T cells, your CD4s or your CD8s to respond and clear that infection in the lung before it gets bad. It also gives you time for a memory B cell response to make more antibodies, which I'll come to.
I want to stop it again real quick. I'm not going to play the whole video, just in parts, because I'm going to make this a 2-section part, and I don't want to lose too many people. It's not like I got a big crowd anyway, but he just mentioned something that was very important, talking about the virus clearing the lungs. See, when people are infected with SARS-CoV-2, you have to go through a process of clearing the virus. And this is what people who think that if the vaccine can't stop the virus, I just might as well go on and just get it. So, you know, that's how dumb it sound, right? Dumb people sound. The thing about it is the vaccine helps you if you do have a breakthrough. If you do have a breakthrough, the vaccine will help you clear the virus faster than a natural infection. You didn't know that, but now you know that. So Aaron Rodgers, when you didn't get vaccinated, that's why you had to miss 10 days, potentially threatening 2 games, which would mean that if y'all lose on Sunday, y'all lost 2 games because you were unvaccinated. Had you been vaccinated, you would have been cleared to play a lot faster because the vaccine would help you clear the virus a lot faster. I ain't got a bookmark it. I already got it. You know what I'm saying? I got the book. I got the books.
B cells, Cd4 T cells, and Cd8 T cells. And that's because antibodies are probably helpful, or definitely helpful, at stopping the virus at the front door. But if the virus gets in and does start an infection, there's actually a lot of time before you end up with a serious lung infection. And that gives plenty of time for your T cells, your CD4s or your CD8s to respond and clear that infection in the lung before it gets bad. It also gives you time for a memory B cell response to make more antibodies, which I'll come to next. So in talking about protective immunity, I'd mentioned these as the three branches of the adaptive immune system, and that was a bit of an oversimplification because antibodies get made by B cells. And so when thinking about memory, that could be...
Antibodies get made by what? What do antibodies get made by, ladies and gentlemen? Antibodies get made by what? I'm gonna give y'all some time. I know CK multitasking. She trying to cook some shrimp fried rice at midnight. Don't ask her why, but she is. No. I'm gonna say it again. Antibodies are made by what? See, this is there what SARS-CoV-2 taught me. I didn't say where they are made. I said they are made by what? Listen. Watch this.
It also gives you time for a memory B cell response to make more antibodies, which I'll come to next. So in talking about protective immunity, I'd mentioned these as the three branches of the adaptive immune system, and that was a bit of an oversimplification because antibodies get made by B cells.
Antibodies get made by B cells. Antibodies get made by B cells. Antibodies get made by B cells. This whole adaptive immunity thing is significantly, you shouldn't be ashamed. This is, you know what I mean? This is us breaking down how the virus behaves. Well, first we had to understand viruses, right? Remember what SARS-CoV-2 taught me, the book. Just remember the book. The first thing we dealt with was viruses. After we get through viruses, the next thing that we dealt with was the immune system, right? The immune system will help us better understand what the virus is trying to do, and therefore we're more understanding of how the virus operates in the body. And we're more understanding of what provides us protection. What type of protection? Is this innate? Is it adaptive? You know what I'm saying? You're going too far. Keep it simple. Antibodies are made. Look.
Infection, and that gives plenty of time for your T cells, your CD4s or your CD8s to respond and clear that infection in the lung before it gets bad. It also gives you time for a memory B cell response to make more antibodies, which I'll come to next. So in talking about
Said it twice.
Protective immunity, I'd mentioned these as the three branches of the adaptive.
So he's talking protective immunity. And he's already said it once. He's going to say it again.
Immune system. And that was a bit of an oversimplification because antibodies get made by B cells.
Antibodies get made by B cells. See, when we start pulling back the layers and diving in a little bit deeper, we began to learn more intricate things that help us fully understand, right? We surface leveled it, then we dug a little deeper, then we dug a little deeper, and then we dug a little deeper. Then we start pulling back layers. Then we're moving the learning curve in other directions and other fields of study. Now we're studying the immune system. Now we're dealing with immunology. First, we were dealing with virology. Then we did with immunology, and then we got into more. An emergence of the two. Then we dealt with virology, right? Then we started dealing with, down the line, we started dealing with all the pseudo scientific claims, and then we get into some bonus stuff.
And so when thinking about memory, that could be generated by either having already had COVID-19 or from getting vaccinated. The potential sources of immunological memory would be antibodies, Cd4, Cd8s, or memory B cells. And so memory B cells are essentially antibody factories with the power turned off.
So when people are talking about their natural immunity and they get to talking or kicking that, I already had COVID, ask them if you or anyone mentioning antibodies or anything like that, just ask them where the antibodies are made. They can't tell you where the antibodies are made, then you really ain't even dealing with much. And then if they tell you if they were asymptomatic, then how do they know they developed any type of antibody response? Or, I mean, if they do have any type of protection against reinfection or anything like that. Like we now know how to counter the ignorance in a sense. This dude said he was watching Fat Beach. Get this dude out of here, yo.
These are cells capable of making lots more antibody if you get infected. They're not actively making antibody, but and since we know that the neutralizing antibodies are functional, having cells that can make a lot more of those is likely to be beneficial. The challenge there is the time delay. So antibodies are usually very valuable before an infection, and they become somewhat less valuable after an infection, again, because the virus is then inside of cells, but still probably valuable for clearing virus outside of cells. So if these are the four components of immunological memory, so protective immunity is going to come from these components of immunological memory. And so that made us ask, well, okay, in trying to understand protective immunity against this virus, one way to ask that is, once you've been infected, do you get reinfected? And how fast might you get reinfected? And we said, well, that protection is going to come from immunological memory. So what we will do is measure these components of immunological memory as a reference point or a surrogate for trying to understand the likelihood of protective immunity being present and for how long. Okay, so we did that, and we did it. So we measured virus-specific memory B cells, antibodies, CD4s, and CD8s, and we did it in about 200 people. This was the largest study ever of its kind for any acute viral infection, to look at all of these components of memory in this many people, and to do so over a 6-month or so window of time. And this window of time was important. We'd love to be able to predict immunological memory at very early time points after vaccination or infection, and we're not able to. It's an important problem. It's one that we and others have worked on, and we haven't solved it. And so we realized, practically speaking, our best way, our fastest way to answer this question was to really wait. Wait 6 months, measure immune memory over that time period, and that would give us a sense of what immunological memory would look like for a period of years. And you'll see that in the next couple of slides. So we did that, and so we measured memory Cd8 T cells, and here's data for that. So each circle is a different person. And we could detect these memory cells in about 70% of people early and about 50% of people late, with a half-life of about 4 months. So not everybody has memory CD8s, but the decline in them over time was fairly slow. And in fact, the half-life that we measured was comparable to the half-life measured for Cd8 T cell responses to a very good human vaccine, the yellow fever virus vaccine. And so that suggests that the memory Cd8 T cells people make after a SARS-2 infection are comparable in their memory quality as that of a good human vaccine. So that was a positive sign here. And in fact, the expectation is that this line is incorrect, basically, and that it probably stabilizes out to a degree later. And so from this, we would expect there to be memory Cd8 T cells probably for 10 years into the future at some level. And then we did the same thing for the memory Cd4 T cells. In this case, almost everybody makes a strong CD4 T cell response to the virus with a similar half-life to the CD8s. And then we were particularly interested in spike-specific virus CD4 T cells and in these TFH because they are important for helping future antibody responses against the virus. And I'll fill in the blanks on that a bit more here. So I talked about how CD4 T cells are important for B cell responses. And this is an animation of some of the complexity there of how CD4 T cells help B cell responses and what molecules are involved. And the way this works is that the T cells and B cells physically interact, but it's not just any T cell interacting with the B cell. It's a specific sublineage of T cells called T follicular helper cells. And that's actually a cell type that's an expertise of my lab. And these T cells differentiate into specialized B cell helpers with specific skill sets and the ability to make particular molecules in particular places. And most notably, to help these rather extraordinary processes called germinal centers, that Facundo Batista is also an expert in, because they're amazing immunological processes to study and important. And their importance one of their amazing features is that they're actually physical structures, microanatomical structures of clusters of T cells and B cells interacting together to make better antibody responses to a viral infection or vaccine. And one of the most amazing aspects of these is that it involves the B cells actually mutating the antibodies in a random way to try and generate better B cells, better antibodies, and then generate memory cells that make those better antibodies. And so those consist of what are called plasma cells, which are the ones actually making antibodies constantly, and then the memory B cells, which I mentioned before. And in a process like this, you can go from an antibody with a certain ability to neutralize a virus to an antibody that has 1,000-fold better ability to neutralize virus on a per antibody molecule basis. You can get incredible improvements in evolution over time in these processes. And so it's important to study them and to know, are there T cells present that can help those processes? And indeed, we observe those TFH cells exist, and memory TFH cells are generated in response to this infection, which was good news. And the final piece of immune memory that we looked at was the memory B cells. And this was actually probably the most surprising finding of our study, which was that after someone was infected and it cleared the infection, the amount of memory B cells actually increased over time. So the amount of memory T cells and the amount of antibodies were decreasing over time, but the amount of memory B cells were actually increasing over time.
Now, y'all heard that. He just sit here and said that the naturally infected people were losing protection, but the memory B increased post-infection. The memory B increased, but the antibodies, right? They waned. They won. Let's hear it again. This is the key in we trying to understand immunity. So this is what we're dealing with.
Memory TFH cells are generated in response to this infection, which was good news. And the final piece of immune memory that we looked at was the memory B cells. And this was actually probably the most surprising finding of our study, which was that after someone was infected and it cleared the infection, the amount of memory B cells actually increased over time. So the amount of memory T cells and the amount of antibodies were decreasing over time.
T cells and memory B, he's telling us the antibodies and the T cells decreased over time, but the memory B cells kept increasing. So the only memory was in the B cells after a certain period of time. The antibodies decrease. The protection is waning. This is a clear case of reinfection. the potential threat of reinfection happening right before our eyes. But let's see, let them continue, and then we're gonna wrap it up.
But the amount of memory B cells are actually increasing over time, being significantly higher at 3 to 6 months post-infection than at 1 month. And this has been recapitulated by many labs at this point, including Michelle Nussenzweig's lab, published around the same time, and Rafi Ahmed's group and others. And so if we take a look at this whole pattern of immunological memory, it's a complicated picture, right? That's the take-home message is really, wow, this is complicated. So here are the antibody responses, here are the Cd8 T cell responses, Cd4 T cell responses, and the memory B cell responses. Again, this is the largest data set ever available, and one of the things that was, I think, pretty obvious when we looked at it was that immune memory is complex. Not all the parts of immune memory behave in the same way, and so one of the key take-home messages there was, what we would have loved would have been to
catch the replay.
We put in all this effort to measure all these different components of immunity, but it turns out if you just measure the antibody titer, that correlates with all of the other things, and so you just can have that simple measure, and that'll be a surrogate measure of immunological memory. And unfortunately, that is not the case. The antibody titers did not correlate well with the T cell levels in given individuals or the memory B cell levels, and as you can see, they also had different kinetics. Lastly, it also shows really the complexity of human immune responses. There was a lot of heterogeneity from person to person, actually 1,000-fold range or close to 1,000-fold range in immune responses in terms of differences from person to person. That's a lot of diversity that we were unable to explain in our study, what the source of that diversity was. But what we could do, and what we felt was important to do, was to try and analyze all of that together and interpret it. And we said, all right, taking a look at all of that data, we can make our best guess as immunologists that these 5 measurements that we made probably contribute to protective immunity in some way. These antibody titers, these memory B cells, the total virus-specific CD4s, the total virus-specific CD8s, and spike IgA. So that if we take those 5 measurements and we look at the population of people that we looked at, either early after infection or 6 months after infection, how many people have all 5 of these potential protective immunity components versus subsets of those, or none. Right? And you can see that there were interesting patterns there. And what was notable to us is that many people do have all 5 of these components, but that there is diversity from person to person. And then lastly, and I think notably at 6 months out, really about 95% of people were still positive for at least 3 out of 5 of these immune memory responses. And to us, that suggests that these people are likely, not proven, but likely to be protected, at least from serious COVID-19 for years into the future, because they had these responses, and the kinetics of the responses were generally showing a very slow decay, right? That is,
all right, what he's talking about is the severity of the infection. What I had to draw out to y'all on a previous show, where I was questioned about where did I get this information from, and well, pretty much everybody in the chat knew that I had the source, but one in particular person wanted to troll and say, I've never heard of this. Where did you get this information from? Why do you think you're an expert? He did all of that on the introduction of the book release, and come to find out, right? The source says people who suffered, had a severe reaction from this, hospitalized, developed more protection than someone who was asymptomatic. And what he's measuring here is the natural infected people between the span of 6 to 8 months post-infection. Are they gaining protection or losing protection? Remember, this whole conversation is about immunity against SARS-CoV-2. And what he is saying to you, measuring an 8-month post-infection, is that he saw a loss in T cell and antibodies in the naturally infected. But the B cell memory, not protection or anything like that, B cell memory increased. There's nothing really to really get at, is the fact that when you're measuring, he's using 6 to 8 months to measure immunity. That's it. That's what his test, that's what the trial was set up for. The trial was set up for to recognize any type of protection between a period of 6 to 8 months from natural infection or vaccination. Doesn't matter. He's doing immunology. This is all about the immune system, the adaptive. So he's trying to see if your immune system is adapting to this virus. And in most cases, what he's seeing is that it's different from persons to person. He's seeing that the only thing that looked pretty steady to him was the fact that there was some type of B cell memory that pretty much was strong or gaining, whereas the T cell was lost and the antibodies was lost, making you susceptible to reinfection. But your body is recognizing it. You know, your body's recognizing it from a B cell level. But nah, I don't want to draw it out. Look, we don't have much more of this video to go. We got 21 minutes of it. I want to pause it because I want to make sure these things digest, and we're an hour and 18 minutes into this particular build. He says, so I need another. No, Pure Black. This is talking about people who have been naturally infected. You was late, see, because you was watching a TV show or whatever you was watching. You was late to the party, my brother. We're measuring immunity. We're dealing with adaptive immunity and immune response. This man ain't telling you to go get another shot, bro. You don't need another shot. When hospitalizations and deaths increase in the vaccinated people, then we'll deal with me. Then I'll deal with another shot. Right now, Moderna has the best protection. But for those of you who have gotten Pfizer, by getting you a booster, your protection and your efficacy and the protection from, Delta variant and all of those things increases. But we don't want to jump out the window with this whole immunity when people don't really understand the immunity. People are, remember, 36% of the people do not have any type of protection against infection. 36% of the people who have been infected with COVID-19 develop no protection. And they're susceptible to reinfection. And it could be either more severe or similar to the previous infection. Your boy Pierce said he got Johnson & Johnson. You need a booster shot. Go get a shot, bro. You need to go get Moderna or Pfizer. You need to make sure, you need to hurry up and schedule it. You need to get that ASAP. You can consult with your doctor, but I'm going to tell you right now, your doctor's going to say, yeah, you need to get Moderna or Pfizer. So you need to go ahead and get you one of them mRNA vaccines. That one shot ain't what's crack-a-lacking. The one shot has the highest breakthrough infection rate, hospitalization rate, and death rate. It is what it is. Yeah, I want you to know you need to know what the antibodies are made in. But what else? What about the thymus? What do we know about the thymus? You have something that is developed in the thymus as well. See, all of that is significant when you're talking about the immune system. You never hear these herbalists or anyone talking about the thymus. But see, when we start slowing things down and have a conversation and learn from stuff, it gets going. He says, got to hit up. Yeah, you better hit up Walgreens. You can get a second Johnson & Johnson vaccine, and your efficacy would increase. The problem is when we get booster shots, the boosters lose, after 6 months or so, the boosters lose their strength. But your initial vaccination is what your memory B remembers. Your boy said, gotta hit up. Yeah, but if I'm you, I wouldn't get a second Johnson & Johnson, although it would increase efficacy. I would just get an mRNA shot. I would get, I said shot. I would just get the mRNA vaccine. I would highly suggest getting the mRNA. Just based on research. I mean, your doctor can, at the end of the day, your doctor can tell you what to do. I ain't gonna be a doctor, but I'm just saying from research. People who've had Johnson & Johnson and got an mRNA vaccine, they've been solid. But look, man, I appreciate everybody for tuning into the part 1 of the adaptive and immune response video. We will kick it off tomorrow, and I'll have a little bit more. I might do it early in the morning, but I want to get both parts out. Just a learning experience here with dealing with the immune system and immune response. And in this particular video, the adaptive immune system. So there were some great things in this video that allowed us to be able to know more, for some people. And you can see that draw out in the conversations in the chat. So I do want to thank everybody for tuning in again. If you have not purchased your copy of What SARS-CoV-2 Taught Me, please do so. The link is in the description. I will be on the Sar Imhotep's channel this Friday doing an interview. Please go subscribe to our Sar Imhotep channel, and I will see you there.